Today we are going to talk about motion, specifically displacement, velocity, and acceleration. So we all kind of have a good idea of what motion looks like, but we just want to be able to describe it as well. So first of all, if I asked you to sit in a chair and not move, you would say, I'm not moving. However, if someone in space knew where you were, let's say you were in Minnesota, and they were watching the Earth spin, they would say, you're moving. So a reference point really takes a look at what is the lens, what's the place or the object is used for comparing if something is in motion. So even though someone is standing next to you says, yeah, you're right, you're not moving. Someone in space that's watching the Earth rotate might say, actually, you guys are moving. And so some examples are you moving in your desk right now or in your chair? Think of a sensor or a phone taking a video. All of those gives us some examples of a reference point. Here is a picture kind of showing and asking the question, are these people moving? So we might say, no, it's a picture. They're still. However, if you were, let's say, outside of the train, you can see in their window kind of this blurry, you might say, yeah, those people are moving. And so anytime that we look at and we try to solve motion questions, we always want to know what is our lens? What is our frame of reference to describe? So our first two vocab words are distance versus displacement. So distance takes a look at how much ground has an object covered, where displacement is how far away is the object from the origin. And so if we look at this with some examples, if I have a situation where this is my start point and I travel this distance and I end up right here, is my distance the same as my displacement? The answer would be no. If I start and end exactly where I began, then I would have what we call zero displacement. However, if I looked at my total ground covered with my squiggles, I know that I covered a really, really large distance. And so we have to be a little bit careful. If we talk about like track problems, oftentimes the displacement there is zero. Distance would be however many laps are there. So that's the difference between distance and displacement is are they going a certain distance? So let's say this is point A and point B. And let's say that this person did a straight line where this is person 1, we'll say. And this is person 2. So they kind of went a weird roundabout way. So do they have the total end displacement? Yes. They're both ending up in B. Did they have the same distance? The answer is most definitely not. Number 2 really went out of his way to take a very weird path, where the other one went more of a direct straight line path. So that's distance and displacement. Taking a look at the example that's below, if Mr. Weemy walks 4 meters east, 2 south, 4 west, and then 2 north, he ends up going a distance of 4 plus 2 plus 4 plus 2, which is 12, but his displacement is 0 because he's just going around the block. Here's another example. If you have a skier that is going back and forth versus at a straight edge, they might have a different displacement or a different distance. So here, if we look, as the skier moves from A to B and then C to D, if we notice, they somewhat backtrack. And so their displacement will not be the same as their distance. Same thing with here. What is the coach's result in displacement and distance of travel as he paces back and forth along the sideline? Well, if we notice, they're kind of just going back, forth. His displacement's not going to be much at all, but his distance will be quite a bit. All right, so here's a graph that we use to calculate speed. So if I ask you, okay, what are some units of speed? Probably the most common one that we know in the United States is miles per hour, meters per second, kilometers per hour. As long as you have a distance over a time, you have a speed. And so we use this triangle to help us figure out, all right, if we're given a speed and a time, we can figure out distance. If we're given a distance and a speed, we can figure out how long it will take to get there. And so this triangle is very, very helpful. Velocity is very, very similar to speed. So speed by definition, how fast an object is moving. Velocity is also how fast the object is moving, but it also adds to it a direction of travel. So if I just say that car is going 60 miles per hour, that's a speed. If I say that car is going 60 miles per hour west, that is now a velocity. And so those key terms, very, very similar, but velocity adds with it a direction. And so again, the hurricane is moving at a speed of 10 kilometers per hour east. Average velocity takes a look at the overall change of time over the change of position. So, examples. A student walks 10 blocks to a computer store. How long will it take him to reach the computer store if he walks 3 blocks in 2 minutes? So, our idea here is that we have a speed that's 3 blocks in 2 minutes. So if we do that and we take 3 blocks, that's our distance. And then we have a time of 2 minutes. So that on average is, we take 3 divided by 2, that's 1.5 blocks per minute. The question is, how long will it take him to walk 10 blocks? So what we would do is, again, if we go back and look at our triangle, distance, speed, time, so I'll put that up here, distance, speed, time, sorry about that D there, and the T. We have the speed at 1.5 blocks per minute. We have the distance. So what we need to do is we would need to take 10 blocks, that's our distance, divided by speed, which is 1.5, and that's blocks per minute. Notice how blocks are going to cancel out and it will only leave minutes. So if I take 10 and divide it by 1.5, it will give me an answer of about 6.6 minutes. Right? So that's how we can use that triangle to our advantage. All right, let's take a look at some other examples. And again, that triangle is very, very helpful to us. It can help us solve as long as we have 2 of the values. We'll be able to solve basically anything that we want to solve. All right, so sorry about the erasing here. But now let's take a look at this one. A student practicing for a track meet ran 250 meters in 30 seconds. So we have some solving to do. This is a distance. This is a time. What is her average speed? So how would I do that? Well, this one is pretty straightforward. It's just simply distance over time. So that would be 250 meters. We want to keep our units. And then 30 seconds. That will give us a value. Let's go ahead and ask Google. Okay, Google, what's 250 divided by 30?
The answer is approximately 8.333333.
Got it. So if we say her speed is 8.33 repeating, and that's meters per second. Now, if on the following day she ran 300 meters in 30 seconds, how much did her speed increase? So now we have a different distance and a different time. So we have 300 meters and we have 30 seconds. This one I don't need to ask Google. I can simply take 300 divided by 30, and I know that that is going to be 10 meters per second. So she ended up increasing her speed by about 1.7 meters per second on day number 2. Our next unit of motion that we are going to talk about is acceleration. Acceleration takes a look at the change of velocity over time. So you've maybe heard the phrase, I can go from 0 to 60 in blank seconds. that is an acceleration because what we're looking at is you start at 0 miles per hour, and you're going up to 60 miles per hour. Remember that that's a velocity. So that ends up being acceleration because you have 0 meters per second or miles per hour, and you have 60 miles per hour, and then you calculate the time. So acceleration can be both positive and negative. Oftentimes we always think of it speeding up, but if you increase speed, that would be a positive acceleration. So the scenario we just talked about with 0 to 60 in however many seconds. Decreasing speed, of course, would also create a negative acceleration. For example, when a plane or a jet lands on a runway and comes to a stop. And so if we look at some examples, or if we look at this in our book, the official unit that we use for the universal is meters per second squared. A very common unit that we use is gravity. So gravity has a acceleration of 9.8 meters per second squared. So in other words, if I go back a slide, this is showing you a rock that is dropped in a well. Did you know that that rock will actually increase speed at different increments as it falls down? So here it's timing it. It's hard to see, but this is at 1 second, it's going a certain speed. At 2 seconds, it's going a faster speed. And at 3 seconds, it's going a faster speed yet. So we kind of see the distance that happens within these seconds. So acceleration takes a look at the total speed or velocity changes in a given time. So let's say we have an example of a driver starts his parked car. So that's key. That means that that car is going 0 kilometers per hour, and within 5 seconds reaches a velocity of 54. So acceleration is the change of velocity over the change in time. All right. So this little delta, by the way, this triangle just means change of. So my velocity, we went 54 kilometers per hour, and we started at 0. So I'm showing you the long way to do this. Our time was 5 seconds, and we also started at 0 because we're starting from a standstill. So in order to figure out, okay, what is my acceleration in that time frame, I would take 54 divided by 5. This one's pretty straightforward. And I would end up with an answer of about 10, and then probably some change. Let's say 10.8. Let's take a look at another one. So here's a falling object. So they drop with an average of 9.8. We talked about that. If an object falls from a tall building, how long will it take before it reaches a speed of 49 meters per second? So this one, we are kind of going to work backwards a little bit. So I want an acceleration of 9.8 meters per second squared. And what it's saying is that you're reaching a speed of 49 meters per second. So what I would need to do is I would take 49 meters per second. That's my velocity. I'm saying that it's starting off at 0. And then I am trying to figure out how long it will take. So this is my change of time. All right. And so what I would need to do in this particular case is I would need to take 9.8 and divide it by 49. Sorry, I'm losing my units. And that will give me my time. So in other words, how long will it take in order to get up to 49 meters per second squared? So if I ask Google, okay, Google, what's 9.8 divided by 49?
The answer is 0.2.
So in other words, it only takes 0.2 seconds to get going that fast. So that just kind of shows us how fast gravity really accelerates objects. So that's our introduction to velocity, acceleration, displacement, and distance.